Okay, let's welcome to our next speaker. Philippe Laborie is going to talk about new results for GEOCAPE observation scheduling problem. Please.
Okay, thank you. So this is kind of incremental work on a quite original problem that was submitted and presented at ICAPS last year. And then we had some new interesting result on this problem. So the overview of my talk will be first to recap the problem itself, description of the problem and the previous result. And then I will focus on our contribution, which is mostly twofold. First, providing some optimality bound on the problem, so some guarantee on the optimality. And the second thing is to find better quality solutions. Okay, so the problem itself was proposed last year at ICAPS by Jeremy Frank and some of his colleagues. It's a satellite observation scheduling problem. Okay, so if to summarize the problem, but it's pretty simple actually to understand, you have a set of scenes to observe by some instrument in the satellite during one day. Okay, and you have n scenes to observe. Each scene is observed multiple times during the day. Okay. Then in the setting of this problem, we assume that all observations have the same duration, which is one time unit. Then the problem is that the scenes are not always observable, okay? Because due to sunrise time, due to cloud coverages, you can observe the scenes only during some periods, during some time slots during the day. And there is an additional constraint that the satellite instrument can only observe one scene at a time. So to have an idea of the problem, here is on this picture, here, an example of, at the same time, a problem instance and a solution. So you see, each line here represents a scene, okay? And then all the empty boxes here are possible slots where you can perform some observation of the scene. Okay, so here in this instance we have a set of about more than 30 scenes that can be observed. And then you see that for a given scene, for instance, this one here, you have a period of observability, but then maybe there is some cloud or maybe some showers during the lunch, and then it's not observable anymore. Okay, and then it's observable again. Okay, at the same time. A description of the problem instance, but also I show here a solution. And for example, the black dots here are the time slots where you observe the scene. So, okay, so you can see that each scene some of the scenes are observed, and then there are some multiple observations of the same scene over time. And you see the additional constraint here that the instrument of the satellite cannot observe two scenes at the same time. So the last line here is, let's say, the activity of the instrument. Okay, you see that in the beginning it do some observation, but here on this whole period it is completely busy doing some scene. Okay, last line is just the union of the observed scene. Okay, so these are the main constraints of the problem. Now what's interesting in the problem is what you want to optimize. What is your objective function? So what's playing an important role in the problem here is the notion of separation time between two consecutive observations of the same scene. Okay, and actually there is a gain related with this duration, with this separation time. It's a piecewise linear function with this type of shape. So it's forbidden. I mean, this separation time must be greater than the threshold as being. Okay, so you cannot observe two scenes too closely in time. Okay, this is forbidden. And then the gain is growing, but after some time, there is a threshold time, after which actually you don't gain anything in observing the scene. Okay? So the objective is to maximize the total gain due to all the separation times between consecutive observation in the schedule. And as you can see, in fact, it's a scheduling problem. You need to schedule the observation activities, but here the number of scheduled observation is unknown a priori. Basically, there is a very simple solution where you do nothing. The gain will be zero. It's a feasible solution. Okay. So in the original papers, the author proposed 44 realistic instances. It covers 2 types of instruments on the satellite and 2 types of science experiments that are called survey and targeted. And then there are also 11 observability scenarios that correspond to some different weather conditions in different months. So in whole, you see it's 2 times 2, 2 times 11 different instances of the problem. In the original paper, the best solutions they were obtained with the time-indexed MIP, a mixed integral linear programming, where the main decision variable are Boolean variable, saying that if a given scene I is observed at the time point G. Okay. And they use the 1 hour computation time, and actually, so solution could be provided for most of the instances, but there were no optimality proof on the quality of the schedule, among other things. And this is this plot I will use. This is the result of the original mixed integral linear program on the different instances. Okay, so the vertical axis is the gain, and then horizontal axis is the months, the different scenarios corresponding to the different months, and this is a combination of the science and instrument. So this is just a reference for the quality of the solutions found by the original MIP. Okay, so the first contribution we did is to try to have some bounds on some upper bounds on the quality you can achieve on the instances. And for that, we tried one thing that is a MIP that is slightly different, which is a disjunctive MIP. So I will not detail it here. I prefer to focus on the other contribution. But basically, the main decision in this MIP will be Boolean variable, saying if the G1's observation of scene I1 is performed before the G2's observation of scene I2. So it's quite large MIP because you have a quite large number of decision variables. Okay, this is a detailed model, but I absolutely won't describe it. But the idea is that this MIP quickly solves some easy instances of the problem to optimality, in particular on a particular type of instrument. But it provides very bad quality for the other ones, okay, and really very bad quality solutions. So, but we had one thing we did is that we relaxed this disjunctive MIP, trying to do something quite simple. Like actually, what is different to model, difficult to model in this MIP is the fact that the instrument can observe only one scene at a time, okay, because you have bad relaxation and so on. So for that, we relax this constraint quite a lot by providing just some energetical relaxation by saying that, okay, you cannot observe more than n number of observations globally in your schedule. And this allows to compute upper bound. And here are these upper bounds we were able to compute. So we see that for this instrument, FR, actually the original MIP was, even if it didn't know it was the optimal solution, was producing optimal or quasi-optimal solutions. So it means that this instance in some way are quite, well, they are already solved by the original MIP model. This one looks more challenging because you see there is a gap, sometimes quite big, between the solutions found by the original MIP and the optimality bound we computed this way. Of course, here we don't know exactly if maybe it's the bound that is bad, but okay. So the second thing we did is to try to produce good quality solutions for the problem. And for that, we are using a CP optimizer model. So for the one who do not know about CP optimizer, it's an optimization engine for solving combinatorial optimization problems. It's available if you have Cplex, for instance. If you're using Cplex, you also can use CP optimizer. And the idea is to have a way to work with CP optimizer that really looks like the way you would work in MIP. That is, it's focused on a declarative model. Okay, so what you do is that you have a combinatorial optimization framework where you declare some variables, some constraints on it, some objective function, and then there is an automatic search that is being continuously improved that will automatically solve your problem. Okay, one characteristic of the search is that it's complete, so if it can eventually prove optimality of your solution. And this is a complete model that we used here. It's quite short, actually. This is really what we rent for solving the problem. I will spend now the rest of the time to describe slightly, give the idea of this model at least. So this is OPL, but you don't need to know OPL to understand this, but this is just to give a rough idea of the model. So there is a first part which is about data reading here. Okay, this is not very interesting, but building some constant structure. Then we define a set of decision variables for the problem, the objective function, and then the constraints. Okay, so if we go a little bit more in detail, concerning the data, we have the origin of the schedule, the horizon. Of course, we have the set of observable time slots for each scene. From this, we can compute an upper bound on the number of observations for a given scene. We do not know how many observations we will use, but we can easily compute an upper bound. Okay, and then we have these two functions of time that appear in the problem, which is the gain function, which is a piecewise linear function. We can define this type of function in the model. Okay, the syntax is not important, but we define this object in the model. We can also define a piecewise linear function that will describe whether or not a scene is observable at a given time point. What's interesting here in this model, we never enumerate the time points, okay? We use functions, so this function will have a number of cells which correspond to the number of observability period. There is never discretization inside of a number of time slots. And the same, of course, for here. Okay, so now let's go into the model itself. Actually, one of the originality of CP Optimizer as a model is that it introduced the notion of an interval variable. An interval variable is a decision variable in the problem, so its value at a solution is an interval of integers, but we also have the notion of optionality. So an interval variable can be optional. It means that there is an additional value in the domain of the variable. That means that the interval is absent. So as all of you here know planning very well, this kind of means that the action is not in the plan. Okay, so it's pretty easy to understand. Okay, so now if you look at the decision variable in this model, first we have two types of interval variables. One for the observation, this AEG. This is it's an interval of size 1, and it represents the observation number G of scene E if E is observed at least G times. Okay, and this is an optional interval because you don't know how many observations you will have on the scene. And then there is another type of interval variables here. They represent the separation time between consecutive observation. Now there is a set of constraints here saying that, okay, so you have this the separation time start at the start time of the observation and it ends at the start time of the next observation. Okay. All these interval variables are optional. Okay, they're not necessarily in the schedule. So in fact, you need to express some implication constraint. And here what we say is that if we perform the G+1 observation, then necessarily we need to perform the G's observation before. So there is an implication that you can write in this way, that the presence of interval AG+1 implies the presence of interval AG. Okay? And in the same way, the separation makes sense only if the two variables are present. So there is an equivalence relation here, presence of AG+1 equal presence of A, linking here these statuses. And now what we say as constraint is that we are missing two constraints. One that says that an observation must, if it is executed, must be executed inside an observability window. This is this type of constraint here. It says that the interval, if it is present, must fit into a segment of the function where it is not null. Okay, so this clearly means that it must be in an observable window. And we have a globally an overlap constraint on all the activities, on the observations of the schedule. This says the instrument can perform only one activity at a time. I will skip, so no, I will not skip this. This is the objective function. It's important. The objective function is to say that, okay, we want to evaluate all the separation time. So this is a function of the length of the observation times, okay, evaluated on function v. And this is a sum, and you can express it this way in the model. Okay. So what I will skip is that a little optimization in the model by considering that in fact there are some properties that tell you that it is not necessary to have an observation in the schedule if it do not provide any gain between the one before and the one just after. Okay, but this is not very important actually. So this is the model itself, and this is the result we got. So this is a blue line here, and we see that okay, for the simple problems it was able to obtain the optimal solutions, and for the most challenging one, you see that we improved quite a lot the result over the original MIP. There is still some gap here, but we still don't know if it is because of the upper bound or because we can still improve a bit the solutions. We also tried an advanced model, but actually it based on this one, but it slightly improved, but it was not something very, very important as improvement. Okay, so as a conclusion, with this SIP optimizer model, we were able to produce near optimal solutions for a gap less than 1% for about 80% of the instances, and then we reduced quite a lot the gap compared to the original solutions. Main interest of this problem of this model also is that it's very easy to extend to additional features. If the duration depends on the observation, then it's just you change your one line in the model. Okay, if you have different observation mode, sequence dependent setup time, etc. So, and the interest also is, as an illustration, it's a good illustration of the versatility of SIP optimizer for solving quite challenging scheduling problems. And if you're interested, there will be material of the tutorial I gave yesterday, which gives a much more detailed description of SIP optimizer. Thank you.
Any questions, comments? I would like to ask you, you mentioned at the beginning that you have realistic instances. What does it actually mean? Do you know? I know it's not about your data, but do you have any idea how it is far from, let's say, real case?
There is someone who can answer much better than me.
So I can tell you more about these later. This was a satellite concept that NASA's been studying. The idea is that it's a satellite that's in geostationary orbit. It has a fine-pointing imager with different sized and geometry of footprints. Its purpose is to potentially study the coastal waters off of the United States and possibly parts of Central America. So the geometry of the instruments, the timing of instruments, scene acquisitions, and the objective function all came from the science teams that are working on the mission. So unfortunately, we don't think it's going to become a real mission, but it's about as real as it gets without being flying. Oh, one other item. Cloud cover for each of the 11 months was derived from GOES data for the North American continent from 2014. And we actually processed that and basically determined whether scenes were visible. And we also have sunrise and sunset data to determine scene illumination at each geographic point.
Good, thanks. Any other?
I'm sorry if I missed this. On the graph you put up on like the last slide or two, where you're showing the optimality,
Okay.
can you give us an approximate amount of time it took to run?
The time it took to run. So yes, we set a time limit of 1 hour as in the original work. One thing I didn't mention is that also in this model, it was able to quickly find some initial solution of good quality. After a couple of minutes, you get already quite good quality solutions. But after, it sometimes keep on improving after more time, yeah. In the paper, there is an example of convergence curve on this type of problem over time, yes.